Hi everyone, my name is Martin Mišiak and I'm a PhD student at the University of Würzburg and TH Köln. And on the behalf of my co-authors Sven Hinze and Arno Fuhrmann, I'll be presenting our work on accelerating rendering of decals. So let's start with a little terminology. What are decals? Decals are simple objects which are used to enrich existing scene surfaces with additional textural information, from buttons on a jacket to bullet holes in a wall. Decals are used to represent all sorts of flat objects where the use of dedicated geometry would be simply too wasteful. Decals usually consist of very little geometry and have a simple shader code. Therefore, they should render very fast. However, before each rendering, a pipeline state change has to be made, as each decal comes with its own textures as well as parameters. In comparison to the actual rendering, these state changes are much slower, and they are the limiting factor here. Our motivation to solve this problem comes from the 3D models used in our research project Realität 4.0. We are dealing with CAD-grade clothing simulations where decals are used to visualize a majority of all small-scale details like buttons or logos, but most importantly, many seams which can stretch across multiple layers of clothing. On average, a full outfit can have around 1,000 decals. And since we are rendering it in VR, we have twice as many draw calls, and the performance requirements for VR are also much higher. So if we wish to render a large number of decals, the number of state changes needs to be reduced. This can be done by taking as many objects as possible and combining them into a single object with a single state. This technique is often referred to as draw call batching and is well known in the games industry. In order to preserve textural information of all individual objects, their textures are combined into a single large texture, the so-called texture atlas. While on a conceptual level the texture atlas technique solves the batching problem, practically there are still a number of problems left, the most notable being the limited texture resolution. One concept that evolved from texture atlases and tries to address the resolution problem is virtual texturing. Similar to the idea of virtual memory, a virtual texture emulates a much larger texture of which only a small fraction resides in actual physical memory. This fraction changes dynamically depending on the currently rendered view and is usually managed via a second indirection texture. In our work, we use the core concept of virtual textures to implement a texture atlas which is sparse. However, we omit the whole complexity of a runtime memory allocation system, which usually comes with virtual textures, as we only need to fill our physical texture once during a preprocessing step. Our technique can be split into two parts, a preprocessing part and a runtime part. During the preprocessing, we take an input model and store all available decal information into two textures. Also, the input model receives a new surface parameterization which is in line with the decal layout used in the textures. At runtime, we then use these information to render all decals in a single draw call. While doing so, we also account for correct texture filtering, which is a bit more complicated due to the use of a sparse atlas. Okay, let's take a closer look at the preprocessing stage. We also refer to this process as baking, since we render out and store values which have already been alpha composited. Our input is a 3D model with multiple decal objects applied to it. The output of our pre-processing stage are two textures, and also an additional set of texture coordinates for our input model. The first step in the pipeline is to establish a correspondence between the decals and the underlying mesh. To this end, we identify mesh patches containing decal data and assign a new set of texture coordinates to them, here denoted as ST. These coordinates need to be unique and non-overlapping, as they will be later used to query the baked information. They can be derived from already existing coordinates or created, for instance, via projection. The coordinates of the mesh patches are then arranged into cells of a square grid in the 0 to 1 range as seen in the picture. Once the patch coordinates are laid out on the grid, the decals in each cell can be rendered. Since decals will only cover a fraction of a cell, we use the sparsity and we further subdivide each cell into a number of tiles. The actual decal baking is done by rendering each tile and shading the fragments with the corresponding decals. We interpret the patch coordinates as vertices and use an orthographic viewport which matches the dimensions of the currently processed tile. Afterwards, the rendered tiles are checked for decal occupancy and non-empty tiles are written into the atlas. Writing starts at the top left position of the atlas, and each time a new tile is added, an X and Y counter is incremented. This way, we can store the incoming tiles at consecutive positions and we get a tightly packed atlas. The disadvantage of such a packing scheme is that the existing patch coordinates can no longer be used to directly query the texels inside of the tile atlas. To solve this, we construct a second texture in parallel, the reference atlas. It can be queried directly using the patch coordinates, and it stores a redirection to the corresponding decal in the tile atlas. Since we use uniform grid cells and the decal tiles have a constant resolution, the references can be stored by directly using the X and Y counters used to construct the atlas. Here, we reserve the value 0 for distinguishing between empty references. The presented baking process performs a lot of redundant work, as it basically renders every single tile in a cell and checks it afterwards for decal occupancy. The total number of rendered tiles can be significantly reduced by first determining which tiles are covered by a patch, as only these tiles can potentially contain decal information. This is done by creating so-called occupancy maps for each patch cell. An occupancy map is created by simply rasterizing a patch in a very coarse resolution which corresponds to the number of tiles in a given cell. It is crucial to employ conservative rasterization for this missed fragments. Since an occupancy map is created, the regular tile rendering process can start. This time, however, we can directly discard tiles which are guaranteed to be empty from the process. Okay, this sums up the pre-processing step. Now, the created atlas texture can be used at runtime to render the baked decals. And this is rather straightforward. As a first step, the reference atlas is read out using the new texture coordinate set. It is important to disable any form of texture filtering on this read, as references cannot be interpolated, for instance like colors. The value read out is the X and Y index of the corresponding tile. In order to determine the exact sampling coordinates inside of a tile, additional information about the atlas is needed. For example, what is the resolution of a single tile, or how many cells was the patch grid subdivided into. For convenience reasons, we encoded these meta information into the last few pixels of our tile atlas. With their help, the final sampling position inside of the tile atlas can be determined. One important thing that needs to be addressed when rendering decals is texture filtering. As decals represent individual objects, a lot of outlines will be present. These are a well-known source of aliasing, particularly if we are dealing with small decals. They cause flickering artifacts, as can be seen here in the video, and this is especially noticeable in VR. A straightforward use of mipmapping, however, can lead to problems. For one, the mipmapping generation process can end up averaging neighboring texels together that belong to different tiles. Another problem arises when filtering at tile borders, and this is due to the sparse nature of our atlas, as spatially neighboring decals can be fragmented across the tile atlas. The solution for the first problem, the tile blending problem during the mipmap generation, is rather simple. Since mipmapping always averages a region of 2x2 texels, This inter-tile blending can be prevented by using only power of 2 tile resolutions. To eliminate the artifacts at the tile borders, however, we need to store additional buffer texels at the edges of each tile. They contain the spatially neighboring texels of a given decal, and they are used to perform correct mipmapping at the borders. The problem with this approach, however, is that we introduce a large number of redundant texels into our tiles. This redundancy increases with each level of supported mipmaps. Depending on the tile resolution and the number of decals in our scene, this has severe implications on the total memory requirements of the atlas texture. In our case, the storage costs of a full MIP chain using buffer pixels was unfortunately out of scope. We ended up storing 16 buffer pixels, which translates to 4 correct MIP levels. However, this was not enough, as we still encountered aliasing artifacts for typical viewing distances. To extend our MIP chain further, we ultimately settled on a runtime filtering approach, and we called it Multisample Mipmapping, or MSMM for short. For pixel footprints that are larger than the available MIP chain, we simply resolve to sampling multiple texels inside this footprint and averaging them. It's basically per pixel mipmapping, but done on the fly. When determining the fixed pixel footprint, we cannot rely on the automatic texture LOD calculation, as the pixel footprint will most likely be scattered across multiple tiles. Instead, we use the coherent footprint found inside of the reference atlas, and we adjust it to the texel resolution of the tile atlas. The scalability of the MSMM technique is unfortunately not quite stellar, as each individual MIP level requires 2 additional power of 2 samples. In practice, this means 4 samples for the first additional MIP level, 16 samples for the second, and 64 for the third. Luckily, the number of samples can be reduced by using other sampling patterns. We experimented with some and achieved good results with 8 rooks for the second level and 8x8 checker pattern for the third level, basically effectively halving the number of required samples for these levels. Okay, let's take a look at the performance of our technique. We evaluated the performance using 3 cloth simulations from a CAD software. Since our technique aims at improving decal rendering, the 3 models were chosen based on the number of contained decals. We have a low decal model with 38 decals, medium decal model with 430 decals, and a high decal model with over 900 decals. The parameters of our texture atlases can be seen on the left. We chose a tile resolution of 128 pixels. We subdivided our cells into 96 by 96 tiles, and we used 16 buffer pixels. Our references atlases had a resolution of roughly 1000 by 1000 pixels, and the resulting tile atlases ranged from 8K to 16K depending on the number of decals. Our test setup consisted of a modern 8-core CPU from AMD, as well as a GeForce 2070 from NVIDIA. The pre-processing times for the 3 individual models were 7.4 seconds for the LD model, 10.3 seconds for MD, and over 38 seconds for the high decal model. For the runtime performance, we measured for each model 4 distinct values. The CPU and GPU times for the unprocessed model, where no baking was done and each decal is rendered on its own, so basically our reference, and they are denoted as decal, CPU, GPU in the graph. And of course, we have the CPU and GPU measurements of our Atlas rendering technique denoted as Atlas CPU and GPU. We can clearly see, when comparing the blue and the gray graph, that our Atlas rendering technique massively improved the CPU performance, basically even allowing an acceptable VR performance for the medium and high decal models. If we compare the orange and yellow bars, we can also see that the Atlas technique improved GPU time slightly. due to the absence of required transparency calculations, and we also did not incorporate specularity into our decals. And finally, we also evaluated the multi-sampled Mipmapping performance. For this, we rendered the high decal model at different distances using either the full MSMM solution or using only the buffer pixel solution. If we subtract both timings, we obtain the computational overhead of additionally performing MSMM. In average, it costs an additional 0.5 milliseconds, and this is for both eyes combined, which was acceptable number to us, especially in respect to the quality improvement it provided. Yes, and that's about it for my presentation. If you have any questions, please feel free to ask them.
Ja, vielen Dank, Herr Mišiak, für Ihren spannenden Vortrag. Während unser Publikum, unsere Zuhörer Fragen bei Slido eingeben, kann ich vielleicht einmal mit einer Frage starten. Wie ist das mit Decals, die vielleicht normalen oder Bump Maps enthalten? Kann Ihr Verfahren damit auch umgehen?
In der jetzig vorgestellten Version nein, aber letztendlich, also wir speichern nur quasi das diffuse Albedo der Decals, quasi in diesen zwei Atlanten. Das heißt, wenn wir jetzt spekulare Eigenschaften oder Bumpmaps speichern wollen, dann bräuchten wir quasi noch zusätzliche Atlas-Paare. Also letztendlich eine Erweiterung dazu wäre straightforward, würde aber mehr Speicher kosten quasi.
Ja, okay, genau. Eine Frage noch von mir. Wie ist es, wenn zur Laufzeit Decals hinzugefügt werden müssten? Vielleicht in einem Spiel zum Beispiel. Gerne mal so ein Bullet-Einschuss oder solche Dinge. Wie würde das mit Ihrem Verfahren funktionieren?
Gar nicht. Also das ist wirklich auf Preprocessing ausgelegt. Es gibt auch Decal-Systeme, die das tatsächlich zur Laufzeit machen und reinbacken. Zu erwähnen wird zum Beispiel das Paper von Chen 2016 und das war quasi für, ich glaube, Far Cry 4 und die haben eine ähnliche Technik, die auch quasi zur Laufzeit entstanden Decals in Atlanten reinpacken konnte. Aber da wir diese Anforderung nicht hatten, haben wir auch quasi es Keep it simple gehalten und es nicht implementiert.
Okay, vielen Dank. Auf Slido hat Anonymous gefragt oder fragt Anonymous, was passiert, wenn der Atlas zu klein dimensioniert wird?
Ich denke mal, es geht um den Teilatlas, nicht um den Referenzatlas. Also quasi, wenn wir zu viele Decals haben, also bei uns ist es implementiert in der Weise, dass der Atlas seine Größe anhand von der Anzahl der Decals bestimmt. Also der skaliert sich automatisch. Und irgendwann natürlich erreichen wir ein Texturlimit. Also für OpenGL sind wir da, ich glaube, bei 16K als maximale Auflösung. Und wenn wir den Limit erreichen würden tatsächlich, dann könnten wir keine weiteren Decals mehr einspeichern. Und die würden dann auch nicht mehr angezeigt werden zur Laufzeit. Also eine Lösung wäre natürlich halt einen zweiten Atlas erstellen, aber ja, ist halt zusätzlicher Overhead und da müsste man schon sehr, sehr viele Decals eigentlich haben, damit man über 16K hinauskommt.
Okay, vielen Dank. Ja, Entschuldigung. Es sieht so aus, als hätten wir keine weiteren Fragen aus den Zuhörern. Damit danke ich Ihnen nochmal ganz herzlich, Herr Mišiak, für Ihren Vortrag und Q&A-Session. Ich danke allen Vortragenden in dieser Session für die spannenden Vorträge, interessanten Vorträge. Ich danke auch natürlich unseren Zuhörern für all die Fragen. Und damit wären wir am Ende dieser Session zu Rendering und Displays. Jetzt